production at Los Alamos National Lab. He's been at the lab since 1990. His main research interests are many. They include phase transitions, optical, electronic, vibrational, transport, and magnetic properties of functional materials, device physics, soft matter physics, non-Hermitian quantum mechanics, which is the topic he will discuss today, geometry, topology, and nonlinear phenomena in materials harboring topological defects, such as solitons, polarons, excitons, breathers, skyrmions, and hopfions. A year ago, he published a book on phase transitions from a materials perspective through Cambridge University Press. He is an affiliate professor at the Royal Institute of Technology, KTH, Stockholm, and he holds adjunct positions at University of Barcelona, University of Crete, Virginia Tech, and University of Arizona. He is scientific advisor to the National Institute for Materials Science, NIMS, in Tsukuba, Japan. He is a fellow of the Los Alamos National Lab, fellow of the American Physical Society, a fellow of the Japan Society for Promotion of Science, and a member of the Sigma Xi Scientific Research Society, Materials Research Society, and American Ceramic Society. How is that? So many honors, many publications, but I don't want to keep us from the science. So he's going to discuss non-Hermitian quantum systems, qubits, decoherence, information, entropy, and beyond. And before I go off to join the audience, Avadh is here for 3 months, so anybody interested in catching up with him, and he has exceptionally good humor. So if you meet him, ask him for a joke.
Do you hear me? Good afternoon, and thank you very much, Mahesh, for a very kind introduction. Before I commence, I would like to take this opportunity to gratefully acknowledge the TSVP very generous fellowship and equally warm hospitality, including from Jonas and Lynn. The topic of my talk today is non-Hermitian quantum mechanics. It's going to be a little bit of esoteric, but I'll try to make it easier. I want to accomplish 3 things in this talk. Number 1, an extended introduction to non-Hermitian physics. Number 2, I want to illustrate it with one example in quantum information about non-Hermitian qubits and how non-hermiticity would actually help with quantum information. Third, myself being a condensed matter physicist, so I must show an example of a condensed matter system. So I will show you a photonic non-Hermitian Kagome lattice and what wonderful things you can do with this. Now, what is non-hermiticity? Any operator, here Hamiltonian, but could be any operator, is not equal to its transpose conjugate. If H equal to H dagger, then we call it Hermitian. If it's not, it's non-Hermitian. All right, so here I say quantum systems, but non-hermiticity need not pertain to quantum system. It could be in classical system. In fact, it has been applied to hydrodynamics, has been applied to population biology, and umpteen other domains of research. So, but in this talk, I'll confine myself mostly to quantum systems. If time permits, at the end, I will come back and touch upon other topics. So let me put things in perspective. Last year was 100 years of quantum mechanics. So 100 years ago, Schrodinger, Heisenberg, and Dirac told us that your operators, including Hamiltonian, must be Hermitian. Why? Because the observable physical world is real. What is observable? Your eigenvalues of an operator. Because everything you observe is real, therefore the corresponding operator, whether it's energy or something else, in this case Hamiltonian, must be Hermitian. Because being Hermitian guarantees that your eigenvalues are real. So for about 70 years, we believed in that gospel, which was true. But who told you that you could not have eigenvalues even if the system was non-Hermitian? That means you could expand the realm of quantum mechanics beyond what Dirac and others told you. And that's the story I'm going to tell you about. Within the non-Hermitian systems, if you have certain symmetries, I'm going to tell PT-symmetry, which means parity and time is reversal simultaneously applied. That will guarantee you that even in non-Hermitian system, those symmetries would lead to real eigenvalues. Now, is it mathematical? No. What that means is that you can have a system with balanced gain and loss, be it quantum system, being electronic system, being hydrodynamic system, where any gain and loss balance is tantamount to having PT symmetry. Okay, so that's where we'll start. And now, before I go, I gave a talk about 16 months ago here in Skyrmions Hoffians, but maybe the audience was partly different. So I want to introduce where I come from. This is Los Alamos, New Mexico. New Mexico is between Texas and Arizona. It's at altitude 7,300 feet. How it was created? Many millions of years ago, there was a series of volcanic eruptions which create one of the second largest caldera, means the dormant mouth of the volcano. And this is the lava flow. Lava is compactified ash, or in geology stuff, UWF. And occasionally we get rain. They are not like here, occasionally. So that rain cuts through these flowing lava. So this is the volcanic eruption caldera. These are the mesas, and the rain cuts and creates this canyon. So this is important because when Oppenheimer was 20 years old, he suffered from colitis, and his father sent him to Los Alamos, northern New Mexico. There was no Los Alamos, but that region for recovery. And he fell in love with these canyons and said, how would it be paradise if I could do physics and live in New Mexico? Hardly did I know that 17 years later, he would be chosen as the director of Los Alamos National Lab. 2 months ago, I was in Australia, there's Oli, and I showed this picture with 3 highest peaks in Australia. That's about the same altitude, about 2.2 kilometers along the z-axis. Now, here's the history of Los Alamos before I go to Non-Hermitian. This is pre-Hiroshima, May 10th, 1945. Original roster of theoretical division where I was. That's Hans Bethe, of course, the Nobel laureate. Also, he figured out how sun makes energy, fusion of hydrogen and helium. His deputy was Victor Weisskopf. After the Manhattan War, he became the chair of physics department at MIT and subsequently the head of CERN in Switzerland, the accelerator. The consultant was John von Neumann, who was largely regarded as the father of computing. Some people have told me and others that they thought that von Neumann was even smarter than Einstein, but that's something else too. Now, until 2 years ago, exactly until 2 years ago, I was the group leader of a group called T4, which is now more than 50 people, but that time there were only 5 people under Feynman. That was my claim to fame, that I was the current group leader that time, but there are no further comparisons. But there were many other very interesting people. There was Rudy Piles, who was lead like in Piles distortion, in dislocations, Piles Nabarro barrier or charge density wave. And he had a student from Scotland, 22-year-old Tony Hilton Royal Skyrmy, who later in Birmingham came up with the notion of skyrmions in field theory. It was the most infamous person, Klaus Fuchs, who allegedly gave the secrets of bomb to the Soviets. Of course, you've read the book by Leonard Schiff on quantum mechanics. And Nick Metropolis, the father of Monte Carlo simulations. And if you're in computer science, the Hamming distance, and so on and so forth. The youngest was 20, the average age was 26 years old. Oppenheimer was 37. This is the original badge. I have my original badge actually here. I cannot get into computers there. This is the old man of 39 years old, Hans Bethe. Feynman, 24, I think. That's Nick Metropolis. I don't know the exact age of Nick Metropolis. Yes. It's Todd Welton. If you go to February 2007 Physics Today, he actually gives his reminiscences of Feynman, how it was to work under Feynman. Very nice. So it's Todd Welton, if it's the same Welton. And there are many others. I could go on, but I also have a view graph after the war in original typewriter, October 1945, but that's for another day. I need to get back to the main topic. That's about quantum information and non-hermiticity. So this is Gordon Moore. You all know who was Gordon Moore? He co-founded on July 18th, 1968, Intel Corporation with Robert Noyce. And I read the business plan. It's 2 paragraphs. We will use semiconductors to make chips and computer memory, and that's it. Now, if you read the business plans of all this techie, Google's 500 pages. So very simple, no nonsense, just the point. Anyway, there's no theorem or anything proven in mathematics or physics called Moore's law. But in the tech industry, because Gordon Moore once said that every 2 years, the number of transistors that you can put on a chip doubles. So that became widely known as Moore's law. Okay. So whether you look at the transistors or how much energy or logical gates, it seems like Moore's law is based, this is pre-COVID. I have data beyond that. Moore's law is now saturating. That means you must go beyond the classical computer or whatever we have done with semiconductors, something beyond. So we must look into new paradigms. One of them is, of course, quantum computing, very hot worldwide right now. Or you can ask how brain with so little power does wonderful computing, how neurons compute. And that's a field called neuromorphic computing. I'm not going to talk about. There's another field called inexact or probabilistic computing, in which you want very cheap things. I want to make decisions about whether I should invest into certain stock or not. I should hire somebody or not. I should fire somebody or not. Doesn't matter. So there you don't need precision. So there's a whole field called inexact computing and possibly other. Similar to classical internet, near University of Chicago, Argonne National Lab, about 30 kilometers or so, there's quantum internet on which we are. So in the future, once quantum internet becomes readily accessible, we'll have completely different way of searching and doing stuff. And is, of course, quantum machine learning, etc. at NASA and other places. So the lab, Los Alamos, was established on April 1st, not full state, but April 1st, 1943. So the second week of April 1983, all the people, or most of the people who were there, including Edward Teller and Richard Feynman, etc., came and gave talks at Los Alamos. This is the talk by Richard Feynman, Tiny Computers Obeying Quantum Mechanical Laws. This was given at Los Alamos. So that's the birth of the notion of quantum computing. Amazing idea how it started. Many years before that, Feynman had given a talk at Caltech, the APS meeting. I don't know why the APS meetings used to be held in Christmas breaks. That's December 29. There is plenty of room at the bottom, and that spurred White House and OSTP to initiate nanoscience and nanotechnology. So Feynman really had wonderful ideas. These are very primitive things I'm showing, but now you have much better hardware for quantum computing. Now, in classical computing, you have up and downs. So that's the only error you make. But the quantum state will live on a block sphere, which means like this. So there are infinite many ways you can make mistakes. So error correction is an extremely important feature of quantum computing. Even if you have hardware and algorithms, how do you error correct? Because you prepare a quantum state, it interacts with the environment, and your information is kind of lost. Okay, so now I'm going to non-Hermitian things. So let me show you a simple experiment. So here are some coupled optical resonators. Red means you have some gain. Blue means you have some loss. They're coupled, and I put them in a lattice. And I pass light this way, and light transmits. If I pass light this way, in the other direction, it does not transmit. So this gain and loss, I'm talking about optics, because Schrodinger equation is analogous to in optics with Helmholtz equation under paraxial approximation. So I will go back and forth between quantum mechanics and photonics, but doesn't matter. The key idea is, so this is an optical diode. It's non-reciprocity. Non-reciprocity of light passing this way versus that way. And there's immense technological implications in terms of optical isolators, controllers, communication. So that's an experiment in which there's a certain symmetry, what I call parity-time reversal symmetry. So let me make it quantitative. This is Carl Bender. We have Ulam scholars at Los Alamos in Center for Nonlinear Studies. Ulam was a great mathematician born in Lvov, which is Ukraine, Poland. Great Fermi-Pasta-Ulam problem, first nonlinear problem. Carl Bender was Ulam scholar 15 some years ago at Los Alamos, and he became my friend because of jokes, not physics, but then we learned a lot of physics, and that's why I got into this field. So what is parity-time symmetry? So Boettcher, who was a student and then came to Los Alamos as a postdoc, wrote a paper in 1998. And they showed that you could have all eigenvalues real even if the Hamiltonian was not Hermitian, and we'll come to that. So what is PT symmetry? So simple things here, momentum and your position. So if I apply the parity operator, nothing has. So X goes to minus X, momentum goes to minus P. If I apply time reversal, X, nothing happens, but P has sense of time, momentum has sense of time, so it is minus P. In order to preserve the probability of a quantum state, therefore, I must also have under time reversal I going to minus I for a consistent theory. Now, suppose you have a Hamiltonian, which is Hermitian plus minus I gamma something I put there. So gamma will be, this is important, gamma will be something like the strength of gain or loss in the system. So the key point is the following: at some finite gamma equal to gamma c, below that, you're guaranteed that all eigenvalues are real, provided you have PT symmetry. At gamma equal to gamma c, that's called exceptional point, and this terminology is important. It's an exceptional point, and it is mathematically interesting, but technologically very important, and we'll see as the talk goes on. Beyond gamma, greater than gamma c means your gain and loss have gone beyond certain amount. At least you will have one pair of complex eigenvalues or more, okay? Some of the notions I'm going to introduce are going to be a bit esoteric or non-trivial, so please feel free to interrupt me anytime if you have any questions. But if I do this, then my inner product has to be redefined. Otherwise, I don't preserve probabilities, etc., which means I must introduce some metric which commutes with the non-Hermitian Hamiltonian, and the metric square is identity. So this is simply put PT symmetry, parity, time reversal symmetry. So the Hamiltonian may not be invariant under either symmetry, but the combined symmetry will keep it invariant, and then you are guaranteed to have real eigenvalues. So this is a picture from, this is what I just said. This is the picture. This is very interesting. In this PRL by Bender and Boettcher, they looked at this Hamiltonian p square minus I x to the power n. N need not be integer, it could be a real number. When n equal to 2, you get your harmonic oscillator. So you know the all eigenvalues are real. So if I now look at the energy, you solve it as a function of n, continuous n. Here's your harmonic oscillator, all eigenvalues are real, etc. But for any other value, you get all of them are real until 1.4 something here, and they stop. And if you go to n equal to 1, you this diverges. But it's amazing that this complex oscillator has all eigenvalues real under these conditions. Before them, there was a French person called Daniel Bessy. I happened to share my office for a couple of days. I didn't know those days. He had numerically shown that this is possible, but nobody believed. Okay, so this remained a mathematical curiosity for about a decade. Oh, this is not useful in physics. Until in 2007, Cristolidis, this person at University of Central Florida, Creole in Orlando, did an experiment on optical waveguides and actually saw everything that was, more or not everything, most of the things predicted by PT-symmetric quantum mechanics. So this is a much later review article in which you see the consequences of PT symmetry in optics. So once this happened, it opened floodgates of technology using non-Hermitian quantum mechanics. So during 2005 to 2015, every 10 years you get the 10 biggest discoveries in physics. Of course, there were Majorana fermions, there were magnetic monopoles in spin ice, or cosmic microwave background. But one of them was parity-time symmetry on optics, this experiment. What that means in optics, if you have PT symmetry, which means your complex refractive index behaves like this. Under PT symmetry, so they start, which means the real part must be symmetric, the imaginary part should be anti-symmetric. Okay, so let me show you one more way of thinking about non-reciprocity in the system. So here is the experiment. So they took two waveguides, optical waveguides, they are coupled. Suppose they're passive, means no gain or loss, and I start here, they are coupled, so the optical power jumps like this. If I start here, it does the same thing. The optical power remains constant, so it's reciprocal, nothing interesting. Now, suppose I take two coupled waveguides. This is gain, and this is loss. When I start here, it's here, jumps, comes back like that. But if I start from here, it goes this way. You see, the optical power oscillates, but at the same time, they're different. That means whether I start a Gaussian pulse here, what is here, matter. So this is non-reciprocal. And the gain and loss in this particular case is less than a critical value. So all the eigenvalues are real. This happens. Now suppose I go beyond this, which you would think is unphysical. So this scale is now logarithmic. So the power increases exponentially, and all the power remains only on the gain side, regardless of whether you start here or not. So this is both cases very interesting non-reciprocal behavior. Remember, gamma equal to gamma C are exceptional point, which I will come back to in a second. All right. So coming back to the comment I made in the beginning, that Dirac, our Heisenberg, Schrödinger said, this is how our quantum mechanics should be 100 years ago. 70 years later, Bender and Boettcher said, well, you can expand the realm of quantum mechanics slightly to bigger space if you have non-Hermitian Hamiltonians with PT-symmetry. So that's this one. That means the PT operator commutes with the Hamiltonian. But then there's some mathematicians who said you can even go further beyond, as long as you have some operator which does this. Basically, if you have an antilinear operator, which basically means this, some antilinear operator on a complex number times a function, complex conjugate of that constant. So this is an antilinear operator. So the simple underlying mathematics was, as long as PT or some other higher operator was antilinear, you're guaranteed all eigenvalues to be real. So original Hermitian quantum mechanics, PT-symmetric quantum mechanics, pseudo-Hermitian quantum mechanics, you still are guaranteed all eigenvalues to be real. Beyond that, it's complex. It's non-Hermitian. Okay, now I'm going to make some pedagogical comments before I go to examples. So what's the difference between Hermitian quantum mechanics and non-Hermitian quantum? As I said, Hermitian, all eigenvalues are real. In general, here you have complex eigenvalues. In typical quantum mechanics, you generate your eigenvalues, in hydrogen spectrum or whatever. Here you don't have your exceptional point. That gamma equal to gamma C is a very interesting thing. I'll come to in a moment. So it changes the whole physics and its implication. So if you have degenerate eigenvalues, you can still find orthogonal eigenfunction. That is not the case in non-Hermitian quantum mechanics. What happens is the two eigenfunctions that correspond to exceptional points collapse. Your Hilbert space becomes slightly smaller. So there's a collapse there. The two wave functions coalesce, and Hilbert space collapses. Here you have symmetric mode distribution. You have asymmetric here. Here you have real eigenvalue surfaces. And here you have Riemann sheets because you're living in complex plane, and I'll show you in a moment what that means. And here in Hermitian, you have continuous eigenstate evolution. Here's something called state flip. I will not spend much time, but I will show you. And of course, here adiabaticity theorem holds. It does not hold in general. So next 2-3 slides are going to be a little complicated, but allow me to tell you something about exceptional point, because this is very important. That gamma equal to gamma C in the complex plane. So as I said, at that place, you are in the complex plane, two intersecting Riemann sheets. So whether I start from red Riemann sheet or blue Riemann sheet, you end up at the same point, doesn't matter. But it's which way in the parameter space you're going, clockwise or anti-clockwise, it matters and determines the physical properties of the system, which were actually in this experiment realized. You have some kind of optical waveguide split like this. So these two modes will propagate this way, but when they go, one of them flips. That means they cannot propagate this way eventually, so there's non-reciprocity. Let me very quickly show what happens. You may not follow the next few graphs, but just what it means, exceptional point. So your Hamiltonian, you're evolving some function of time, and there's an exceptional point gamma equal to gamma C. In this case, that happens to be some parameter xi equal to I. So I can go around like this or backward like this, which means Now I have two intersecting Riemann sheets. Whether I go like this versus like this changes the properties and propagation direction and the reciprocity. One more complicated wave, and then we'll come to examples. Now, if I evolve the system, don't worry about looking at this thing. Only thing you need to look at it, if I'm going backward, it's like this. Forward, I go like this, and I come here, and I have to jump to next Riemann sheet. So this is called state flip in non-Hermitian quantum mechanics. What that means is backward, this red thing is a continuous evolution. If I go forward, here I go, and suddenly I have this jump from one sheet to another. It's called anti-adiabatic state jump. This is a property of non-Hermitian systems. If I get time, I will explain. Otherwise, just to tell you that what we call the exceptional point has immense fundamental importance, but these things means technology, what you can do in complex. Okay, now I'm going to start with an example in quantum information. And I'm going to take a two-level qubit. Could be photonic, could be superconducting generic qubit. And I will take one Hermitian qubit, then I will take one PT-symmetric qubit. Means the PT operator commutes with the Hamiltonian. Okay, and then I will take something called anti-PT-symmetric qubit. That means the PT operator anti-commutes with the Hamiltonian, and show you when I go to real properties, decoherence, entanglement of these qubits, non-Hermitian means PT and anti-PT qubits are better than typical Hermitian qubits. So let me explain in physical terms what I mean by PT and anti-symmetry. So I told you PT symmetry means balance, gain, and loss. So you have two waveguides with balance, gain, and loss, some coupling kappa, and they interact with the environment. So if I reverse gain and loss, I get this. So basically, when you flip gain and loss, system remains the same. So that's PT symmetric. PT operator commutes with the Hamiltonian. Anti-PT means the coupling is imaginary, and gain and loss, gain. Now if I flip, it becomes loss with minus here. So this is very different. This physically means the PT operator anti-commutes with the Hamiltonian. So more formally, yeah, PT symmetric and anti-PT symmetric. This means PT square equal to +1, commute, and then I will calculate something called phase function in a moment for this qubit. And then I'll have to look at the reduced density matrix. When you want to evolve a quantum system, you go from wave function to density matrix. And reduce means you trace over the environment, so you find some function. In this case, eigenvalue could be ±1, anti-commutes, and now you get difference between two phase functions. And this you cannot do with true non-Hermitian systems. So you have to invent another technique. We will not take you through that. It's called time-dependent Dyson map. What that means is any non-Hermitian system, you want to bring its density matrix to look like a Hermitian system so that you can do the typical Hermitian. So I'm going to do this. There will be some equations, but that's okay. So PT was gain and loss. Even anti-PT symmetry can be realized in experiments. Here you have some whispering gallery mode with a tapered optical fiber with the two resonators which are coupled, and I'm not going to go into details in the context of time, but you can synthetically realize anti-PT in optical microcavities. All right, so once this happened, people could find not just PT symmetry, anti-PT symmetry, just about everything experimentally. So you can, and there were papers beforehand which talked about how PT or anti-PT symmetry could improve quantum information. So there are many, many papers showing that. So now, next few equations, I'm going to do some real technical thing and take three different kind of qubits, really. So this is a Hermitian qubit, so it's like two-level system, alpha and minus alpha, and this is the coupling, okay? And you can check if I do transpose conjugate, this is Hermitian. Then I'm going to slightly change this part as imaginary. And then you can check this particular Hamiltonian 2x2 is PT symmetric. You can check it. And if I do something different here, is the most general qubit 2x2 matrix. This will be anti-PT-symmetric. You will find that this will anti-commute with the PT operator. So I'm going to take this all these three cubic systems, couple it to some bath. And bath consists of some bosons, phonon-like thing, very weakly coupled in this fashion. So coupling of bosons to these qubits. Without going into too much detail, I want to show you why these qubits are better than this in terms of real quantum entanglement, entropy, etc. So first thing, very quickly, I want to diagonalize all of them. So this similarity transformation will do this. All these three qubits are now diagonalized, and this omega naught that appears, which I'm going to call qubit parameters, looks like this. All three positive, one negative, two negative. Hermitian, PT-symmetric, and anti-PT-symmetric. And now I'm going to evolve the system without going into details, so don't worry about these equations. I'm going to write the corresponding reduced density matrix. So density matrix for a given wave function, you can define like this. So it's a probabilistic way of thinking about quantum states. You can, if it's the one state, you have pure state or a mixture of states. So you write the density matrix for all those three qubits, and it looks like this for Hermitian and PT-symmetric cases. They are similar. You don't need to know all these equations, but the four components, 1, 1, 2, 2, and off diagonal. In off diagonal, there is gamma t, some function that captures the decoherence properties of the qubit or the quantum state. Then some omega, which captures the phase function. And this is simply the spectral function of the bath, not so important. So this is the thing I want to pay attention to. You don't need to know all this detail, but the coefficients appearing here, if it's theta, it is PT-symmetric. If it's nu, it's Hermitian. But if you want to do the same thing, one more view graph, for anti-symmetric, you cannot do it, because then you have to go to general non-Hermitian system, which is very complicated. So you have to invoke a different technique called time-dependent Dyson map, which you can find in one of my papers. But you can again find this thing, and again you see the decoherence function, but now you have two phase functions, and their difference will tell you the properties, which we'll come to in a moment. And that's the decoherence function. Okay, so now I'm through with these. So now we can understand decoherence in these three qubits. So that's a decoherence function, e to the minus omega naught square. Omega naught was the qubit parameter, which depends on the parameters in the 2x2 matrix for each. And that's the decoherence function. So now I'm going to plot this as a function of time for the three cases I showed. Green one is Hermitian, which means as time goes, the system decoheres very fast. We don't want that. Decoherence is very bad for quantum computing or any other application, because the moment you create a state, it decoheres, so you lose information, lose quantum information. So you want this to last longer. The blue one is the PT-symmetric case, so it's slower than this. So I've improved upon decoherence of that qubit by making it PT-symmetric. If I make it anti-PT-symmetric, this is the red curve. That means now the quantum state that I prepared stays much longer. So this is clear benefit. Now, why did this happen? Without going into too much detail, you see, for the Hermitian case, you have all these parameters with plus. For PT-symmetric, you have 2 pluses, 1 minus. That means delta square plus psi square should be greater than theta square. Otherwise, this is imaginary. So this equal to theta square is your exceptional point, okay? Here, in anti-PT, the red one, you have two negative signs, so alpha square should be greater than summation of these two. There are 2 degrees of freedom to counter decoherence. So the point I made here is, by creating PT-symmetric, anti-PT-symmetric, non-Hermitian qubits, I have improved the decoherence property of a qubit. That's very desirable. Another way of quantifying this is von Neumann entropy. Yes. Yes, so yes.
Disturbed perfect thermal bath.
Okay.
How
so,
this?
So I'm comparing apples with apples and not oranges. The bath is exactly the same. The system parameters are chosen such that the comparison is the same. So the only thing that matters, I mean, this is a good question. How do I compare? So bath is the same, very weakly coupled to the qubit, and other parameters are such that basically I ask for deviation from hermiticity. And that's basically, this is deviation from hermiticity. PT-symmetric is less deviant from hermiticity. This is much more, and that improves decoherence property. Okay? But I have the same bath and same other parameters, so I'm comparing apples with apples. Okay? Or we can discuss more later if that's not the case. Another way of understanding the decoherence is through von Neumann entropy. And so again, using those qubits, I can write the corresponding functions and the entropy in this fashion, where this is the reduced density matrix, and you get some expression like that. Doesn't matter. What matters is if I now plot it for 3 qubits, now plot it for 3 qubits. So this is my von Neumann entropy as a function of time. Again, Hermitian. So this you start from 0, and this is basically log of 2, which is here. Yeah. So it saturates at log of 2 from the previous expression. So this quickly goes to this. The PT-symmetric takes more time, and the anti-PT-symmetric takes even longer time. So this is basically the same information that I had in the previous slide, captured from von Neumann entropy point of view. Basically, some measure of entanglement. So again, from this measure, the non-Hermitian qubits are better than the Hermitian qubit. What else can I do with this?
So just to understand the previous one. So when you're talking about von Neumann entanglement entropy, you're now considering this as a reduced density matrix, and you've traced it. You're now considering this as a reduced density matrix, and you've traced out the bath. Is that...
Yeah. So I'm using reduced density matrix. That means I've traced over the environment and the bath. Yes. Yes. Exactly. Otherwise, yes. Precisely. Now the next way in quantum metrology is the Fisher information. You know, how do I quantify whether the state that I have created, how precisely I can measure, how stable, etc. So the relative entropy mathematically is called Kullback-Leibler divergence. You don't have to worry about that. But once you know the reduced density matrix, for some parameter k, you can calculate that. So the two parameters of importance here are temperature, T, which is 1 over beta, and what I call the qubit parameter, omega naught equal to square root of alpha, beta, whatever, square roots. So one can calculate. So I want to know for these 3 qubits, if I calculate the Fisher information in terms of Fisher information, how precisely I can measure temperature or the qubit parameter. So without going into details, I have all these things. I do it for temperature and qubit parameters, and this is what I find. So the Fisher information, if I look at inverse temperature for 3 cases, so you have the Hermitian, you have PT-symmetric and anti-PT-symmetric. You can't quite see, but this maximum is slightly higher than this maximum, slightly higher than this maximum. So there's a gradual increase in the Fisher information with respect to inverse temperature. That means you can more precisely estimate temperature in the case of anti-PT, but you look at the variance and the area under the curve, which is much superior. So again, from metrological point of view, quantum metrological point of view, non-Hermitian qubits are better. Same thing you can do with respect to the qubit parameter. It's very, very clear that not only the area, but the variance, the maximum, everything is much superior for the PT qubit compared to Hermitian, and anti-PT is much more superior. So in terms of capturing the precision by which you can measure temperature or the qubit parameter is good. Let me skip Renyi entanglement entropy. So that was one example just to illustrate that to get over decoherence and entanglement of qubits for quantum computing, if you made non-Hermitian, particularly PT or anti-PT symmetric qubits, they are better. That's one. Now I'm going to dwell into a different example of PT symmetry using a photonic Kagome lattice as an example. So why Kagome lattice? Kagome lattice in magnetism is very frustrated, as in many other applications. This is photonic. So these vertices here, don't look at red and blue yet. These vertices here are optical waveguides coming out of the board at you. And you can synthesize them now. So the problem is, if you take a square lattice, I can put blue means gain, red means loss. I can put gain and loss, and you can check that lattice becomes PT symmetric. You can check that. I tried for months with Vavedt trying to make this lattice all kinds of configurations of gain and loss, and it was not PT symmetric. What does that mean? That means if for gamma equal to 0, it was there, but not for any finite gamma. You could not make the lattice. Because I said you must have finite gamma less than gamma c, under which all the eigenvalues are real. And we couldn't do that. One day, Vavedt came running to me saying that, oh, he found some papers in which they had dimers on a ladder and it became PT symmetric. And why don't we try dimers? So what we did, we put gain and loss. So actual waveguide would have been at the vertex, but now we put gain and loss dimer. Dimer means the red is a waveguide coming out at you. Blue is a waveguide coming at you in this particular configuration. So what I have done is I've created two Kagome lattices twisted. One is this way, left, and one is right. So one is the gain sublattice, another is loss sublattice. And here's the tight binding model. You have hopping here, closer, more hopping, further, less hopping, and these dimers are coupled. Gain and loss is coupled. Okay. So let me just show you a few things in this lattice. So as I said, for optics, the Helmholtz equations are like Schrodinger equation in the parametric approximation. So I can write down the optical intensity here like this. So two components you can write on that lattice, which I showed. Now you take its Fourier transform, do stuff, and you can calculate the dispersion relations. And this is interesting. So, no. Yeah. So this is for gamma less than gamma c. That means the gain and loss are below the exceptional point, below a certain value. You will see two copies of what you see in a typical Kagome lattice. So you will see one Dirac point here and one you cannot quite see. So two Dirac points, two flat bands. See this one, and there's a gap in flat band. So because the two lattices are coupled, so you have flat bands. And then you have what is known as quadratic touching point, which is topologically non-trivial. So you have two topologically quadratic touching bands here and here, and two one-way similarities. So basically, this picture dispersion tells you two Kagome lattices interacting with each other. Now, so all eigenvalues are real. So this is along the Brillouin zone. Everything is good. Now I'm going to increase gamma to gamma c. So I'm going towards the exceptional point. When I do that, this gap goes to 0. The gap between the flat bands goes to 0. It's very interesting. And it's completely gone to 0. And these bands also become dispersive, more dispersive here. And then I go beyond gamma, more than gamma c, which means you must at least have a couple of complex eigenvalues or more. So here I show both real and imaginary part of the eigenvalues, okay? So, and for this particular case, gamma c is about 0.8. The reason is I'm going to show you what this does to physical system in next 2 or 3 slides. So one thing, so time in Schrodinger equation becomes propagation direction z along this waveguides, okay? So that's the thing you need to keep in mind. And now I'm going to look at power along the waveguides as I'm going. And you can excite either with a wide beam at the beginning of the waveguide or a narrow beam. And you see the power oscillates as you're propagating along the waveguide in a particular way. And if I make it narrow, other modes are generated, and it's rotating and propagating because of this. So that you can see in the following fashion. So this is the cross section of the whole system. The waveguides are coming out at you. So this is passive, no gain and loss. So the system remains in some homogeneous state. If it's slightly below the exceptional point, then you see the power in this dimer is coupled and inhomogeneous. Here, you're radially across the waveguide. So as for different distance from the start, it just decays radially. But in the case of PT-symmetric, slightly below the exceptional point, you see multiple branches. And these multiple branches are telling you that there's a rotation of power as you propagate within the waveguide. So very non-trivial things. And here you can see one example. So in the passive array, when you're propagating, the modes keep doing like this, but nothing interesting happens. But when you have non-hermiticity or PT-symmetry, the power goes like this, then like this, so it has chirality. So this non-hermiticity has induced chirality in the mode propagation in this. So this is just to illustrate within a condensed matter optical setting that non-hermiticity can lead to unusual phenomena. And so, okay, so I could go on, but I will stop at this second example, and I just want to make a few remarks about that. So one is advertisement. In 2018, we started quantum summer school at Los Alamos for senior undergrads and graduate schools from all around the world. We get about 1,000 applications and we pick up 25. But these people are absolute experts in quantum computing. This is from 2024. We had fantastic speakers. Aronson, Martinez got Nobel Prize last year, Peter Shor algorithm. So I encourage students here, those who are interested in quantum computing, to apply to this summer school. This year we have the, I think, 9th one. Couple other remarks without making any scientific comments. I'm not going to explain anything. We have also looked at what happens to quantum chaos with non-hermiticity, and you can actually enhance quantum chaos. I'm not going to go into detail. Or if you want to create periodic states in stochastic qubits, you can do all that. All right, one final remark. I said non-hermiticity is not pertinent to quantum mechanics. You can do in other systems. This is a very simple example of PT-symmetry in biology. Of course, the first time it was applied to population biology. Here what you're saying is this B is bacterial field, many bacteria swimming. And then you have the C. elegans worms together, okay? And how they swarm and move. So this is worms moving, this is bacteria moving, and how they travel. This actually, if you look at this paper, is exactly PT-symmetric swarming motility. So biology makes, I mean, there's nothing to do with quantum mechanics, but the gain and loss in a certain way. In biosensing applications, PT-symmetry or non-hermiticity is very important. And I have been looking with some medical researchers recently that you have many mitochondrial diseases. So mitochondria has electron transfer chain, which actually is truly quantum. It's an open set, biological systems are open. So maybe understanding non-Hermitian quantum mechanics within mitochondria could help understand certain mitochondrial-based diseases. With that, I'm not going to say this, basically, that non-hermiticity is useful in enhancing decoherence and other properties. And this is not just applicable to quantum or other systems. You have electrical systems, magnetic systems, plasmonics, metamaterials, even hydrodynamics. So non-hermiticity or PT-symmetry, etc., is very useful, and therefore you can become a quantum hermit. Thank you for your attention.
Questions, comments, anyone?
Yes.
Thanks for the wonderful talk. I have a question about the photonic lattice. So in the z direction, the dispersion is completely flat?
No,
No.
the dispersion was in this plane of all the waveguides I was talking. Z direction is the propagation. Dispersion changes as you go. Dispersion changes, the power changes. Yeah.
Right, so there is no dispersion along the z direction, right?
Okay.
I mean, z
across this
perpendicular to
dispersion, it may change a little bit, but not much along the
okay,
propagation direction. However,
okay.
the power changes. Yeah.
So can you explain a bit more what causes this chirality of the power?
Oh, because when you are below gamma equal to gamma c, there are certain modes which get excited as you propagate. So sometimes I showed you the oscillatory power. Sometimes it picks up left chirality, sometimes it picks up right chirality. Fundamentally, the way I set up the Kagome lattice was two Kagome lattice, one left-handed, one right-handed. So that is now reflecting in the propagation of power along the waveguides. That's the original. Let me, if you're not clear, it's, yeah, here is the, you see, the reddish and the bluish, there are two sublattices. So the chirality is built in the way I created this structure. And that reflects in the propagation when you have non-hermiticity. I mean, because it's gain and loss, so you have non-hermiticity. So that's the origin of chirality.
Could it be connected to some very curvature type of thing in this two-dimensional bands?
Could it be connected to what?
Like very curvature, quantum geometry.
You say curvature? Possibly. I mean,
Okay. I would like to.
Yeah. There are also PT-symmetric in curved system, but this could also be related to some effective curvature, but that's a different topic. But Reuter in Germany has actually synthesized all these things. You know, so you can do all the experiments now. What this theory predicts. Yeah.
Thank you.
Yeah. Yes.
Okay, this is a very naive question, but the anti-symmetry, couldn't that be related to non-commuting variables underlying it?
Absolutely right, because that's anti-PT-symmetry means anti-commutation relations. So there is some underlying algebra that one could write. Yes. There's a person in Czech Republic, Czech Academy of Science, Miloslav Znojil, Z-N-O-J-I-L. He actually looks at these kinds of questions, very mathematical, but fundamental to this. Yeah. Thank you. Oli?
So when it comes to the decoherence with the PT and that anti-PT qubit, are we just getting a free lunch by going to the decoherence? It means that we're getting more information over that.
No. Decoherence means I'm losing information to the environment. My putting gain and loss means PT-symmetry is some way of stopping losing this information to the environment in a slower fashion. So,
okay.
So that's a way, it's countering losing information to the environment.
So is there any downside whatsoever?
No.
Is there something?
Okay. So first of all, no free lunch. We have ways of turning the knobs on decoherence by using balance gain and loss. So that's something useful. Now you're asking, is there a downside? Are there side effects of this medicine? Okay, which I have not explored yet. Not everything, I'm sure, not everything in non-Hermitian quantum mechanics is good, because there are some other effects. I mean, the field has evolved quite a bit, both mathematically and in terms of technology over the last 20 years. Yeah.
Further questions? If not, let's thank Avadh once again.
Thank you.